Welcome physics people to today's video. In today's video we'll be looking at horizontal projectile motion. And to get us started, let's consider a nice compilation of vehicles running off cliffs in a projectile motion manner. Enjoy!
Gotta get that. I like that boom boom pow, them chickens jacking my style. They try to copy my swagger, I'm on that next shit now. I'm so 3008, you're so 2000 and late. I've got that boom boom boom, that future boom boom boom. Let me get it now, boom boom boom, boom boom boom, boom boom boom, boom boom boom. Gotta get that boom boom boom, boom boom boom, that boom boom boom. Yo, I've got that hit that beat the block. You can get that bass on below. I've got that rock and roll, that future flow, that digital spit, next level visual shit. I got that boom boom boom, that boom boom boom. People in the place, if you want to get down.
Nothing like a bit of high-speed action to get you in the mood for some horizontal projectile motion. Shortly, we'll be looking at the Harvard University shoot and drop apparatus and an experiment that they've carried out to investigate horizontal projectile motion. We'll then move on to physics classroom and have a look at one of their projectile simulators. Then we'll have a look at my favorite, the PhET projectile simulator. And finally, we'll look at some sample calculations using horizontal projectile motion. So first, the Harvard shot and drop apparatus. The device consists of a spring-loaded iron shaft, and on the left-hand side we have one end protruding, which a billiard ball is placed upon. Now when this device is operated, the pin will be removed from the ball and it will free fall to the ground. On the right-hand side we have another ball being placed on a mount. This time a bolt will be fired, which will give the ball a horizontal velocity to the right. The device is designed to fire both balls simultaneously. The one on the left has an initial velocity of 0 and is accelerated downwards towards the ground at 9.8 meters per second. It moves purely in the vertical orientation, whilst the right-hand side ball has constant velocity in the horizontal plane, yet accelerates in the vertical plane, also at 9.8 meters per second in a vertical direction towards the ground. Let's now examine this projection in slow motion. As can be seen, both balls accelerate towards the ground at 9.8 meters per second. Another way of analysing this horizontal projectile motion is to use the physics class simulator. So you have here in front of you an object that's elevated above some reference height. You see that we have an initial horizontal speed of 40 meters per second to the right. There's no angle of inclination and it's elevated at 120 meters above our reference height. Let's trace that path. Let's take that back to the start. Let's consider acceleration. The object accelerates at 9.8 meters per second downwards in the vertical direction for the entirety of the journey. There is no acceleration left or right in the horizontal plane, as it is a constant velocity. Finally, let's have a look at showing the velocity vectors. At the start, we've got no velocity in the vertical direction whatsoever, but we do have a velocity of 40 meters per second to the right. First of all, let's consider what's happening to this horizontal, the magnitude or the size of this arrow throughout this simulation. You can see that it's staying the same, nothing is changing at all. That represents a constant horizontal velocity to the right of 40 meters per second. However, let's now consider what's happening to the vertical velocity as this object goes over the edge. It starts with a vertical velocity of 0, but once we run this simulation, you'll see that that increases immediately. So it's getting larger, reaching its greatest velocity upon impact. So at the end of the projection, we can see you have a component of the velocity that's traveling to the right, that being 40 meters per second, and also a component of the velocity traveling downwards, which we can calculate using the Suvat equations. Let's further examine our projectile motion using the PhET simulator for projectile motion. So we have a cannon that can be elevated, and we're going to give an elevation of, say, 10 meters. We're going to change our angle, because this is, of course, horizontal projectile motion, to 0 degrees to the horizon, and we can set our initial speed to whatever we choose. So let's choose 20 meters per second. There's a range of different settings we can have. Let's be more exciting than just a cannonball. Let's fire a human. That's pretty exciting. So we hit our fire button, and out goes our human. And it's got a range of roughly 28.5 meters. Summarizing our findings, we have on the right hand side of the screen a diagram of our projectile motion as an object shoots over the edge of an elevation and accelerates down towards the ground and making impact at its lowest position. This can be broken up into a vertical component or direction. So we find as the object drops, it falls to the ground at exactly the same rate as the object that projects over the edge of a height falls at. And also horizontally, we find that the object moves to the right at a constant speed at exactly the same rate as the object falling over the edge does. In terms of vertical direction, when the object moves over the edge of the elevation, it has an initial vertical velocity of 0 meters per second. It has a constant acceleration towards the ground of 9.8 meters per second, and this can be observed by the distance traveled in each of these time intervals. It's getting greater and greater. Therefore, the object is accelerating. Because it's undergoing constant acceleration, we can use the equations of constant acceleration, commonly referred to as the SUVAT equations. This is involving the displacement, the initial velocity, the final velocity, acceleration, and time. Next, let's look at the horizontal direction. Horizontally, the object moves off the elevated edge at a constant velocity, and that's maintained for the duration of the motion as the object falls to the ground. We can consider its horizontal component as a constant velocity moving to the right. So there's no acceleration whatsoever. Accordingly, when we come to calculations, we can simply use the speed, distance, and time equations, which are appropriate for constant velocity. It's worth mentioning that the vertical and horizontal motion can be considered independently of one another. We can perform calculations in the vertical direction, such as the impact velocity vertically or the time vertically. We can also perform calculations horizontally, such as speed, distance, and time. Importantly, the time required to complete the journey is the same for both vertical and horizontal motion. If this is our projectile motion and it takes x units of time to reach the ground from the position it started, it will also take the same x unit of time for an object to fall from the elevated position straight down to the same vertical displacement. And likewise, it will take the same x unit of time for an object to move horizontally at a constant velocity, reaching the same location horizontally as the projectile. Finally, the final or impact velocity is the vector sum of both the vertical and horizontal velocities, and that can be found using some simple Pythagoras. Let's now look at some practical examples of horizontal projectile motion. Okay, our task is to find the range of the projectile. So what we have is an elevated projectile, 10 meter elevation, horizontal projectile motion, no angle of inclination, and this object will shoot and will create some kind of range. So let's have a look at this problem. So the range is from the beginning at the base of our projectile to where it lands. And let's have a look at that motion. First of all, let's consider the vertical motion in isolation. Vertically, that motion is the same as an object simply dropping from an initial speed of 0 and accelerating at 9.8 meters per second towards the ground. So we have constant acceleration in the vertical motion, most important. Knowing that, we can approach this with a SUVAT approach. So the equations of constant acceleration. We have an initial velocity of 0 at the start. This cannonball in the vertical direction has a speed or a velocity of 0. It's displaced during its motion by 10 meters from where it started down to the bottom. Now notice, because the initial velocity of this ball is going downwards in the vertical, I'm going to take downwards as a positive direction for the notation of all the values I put in for my variables for the SUVAT equation. So the displacement starting at this position here moves downwards to the ground is a positive 10 meters. Likewise, the acceleration, because it's operating down towards the ground, is also 9.8 meters per second squared. It's a positive value. In order to calculate the range of this projectile object, we need to calculate the time it takes for a cannonball to fire from its initial position all the way to its projectile landing. So we're going to consider the vertical motion. Initial of 0, a displacement of 10, an acceleration downwards of 9.8 meters per second, and I wish to calculate the time it takes to make that fall. Remembering it takes the same amount of time for an object to fall from this point to the ground as it does with a cannonball with a horizontal velocity to also fall to the ground on this trajectory. So let's use our SUVAT equation. The appropriate equation is S equals ut plus a half at squared. It uses all the variables we have on the left hand side. So let's sub in our values. S becomes 10, U is 0, A is 9.8 and T is our unknown quantity. Let's simplify. 0 times T becomes 0 and a half of 9.8 becomes 4.9. So we have now 10 equals 4.9 T squared. That leaves us with T squared equals 10 divided by 4.9. If I take the square root of the 10 over 4.9, I end up with a time of 1.43 seconds. And that represents the time it takes for a stationary object to fall 10 meters when accelerated by 9.8 meters per second. Okay, so an object falling from here would take 1.43, and an object projected with horizontal velocity will also take 1.43 seconds to reach the ground, regardless of its horizontal velocity. So step 1, we've calculated the time it takes for an object to complete this projection. Now let's consider the horizontal motion in isolation. Horizontal motion, of course, has constant velocity. There is no acceleration in the horizontal direction. So we have a constant speed of 20 meters per second, as stated down here as our initial arrangement. That's constant for the whole projection. We know that the time it takes for an object to start here and to project to here is 1.43 seconds. So that's also the same time in the horizontal as it is in the vertical. That links the two planes. And the displacement or the range is what we're calculating. How far has this object moved in the horizontal direction? So simply, speed equals distance over time. We use this fundamental equation because we're not accelerating. We don't need to use the equations of constant acceleration with the SU's, V's, A's, and T's. What we use instead is the basic speed equals distance over time. So we sub in our values. The speed was 20 meters per second, displacement was the unknown, and our time was 1.43 seconds. We do our mathematics and we find the range of this object, or rather the distance in the horizontal plane from where it started to where it finished, is 28.6 meters. A second and final question that you might be asked with horizontal projectile motion is to calculate the impact velocity of the projectile. So let's consider this scenario. There's our projectile, and we'd like to know what is the actual velocity upon impact. So we've already done our analysis of the vertical direction of motion, whereby we have constant acceleration. We have an initial speed, we have a displacement still of 10 in the vertical direction, an acceleration of 9.8, but this time we'd like to work out what is the velocity in the vertical direction. So we're looking at just before it hits the ground, what's the vertical velocity of this object? So we can use our SUVAT equations, and in this case we've got v squared equals u squared plus 2as. Let's sub our values in. We find that v squared equals 0 squared plus 2 times 9.8 times 10, which can be simplified to v squared equals 196. So we take the square root of that and we end up with a velocity of root 196, or rather a velocity of 14 meters per second. So the impact velocity in the vertical plane is 14 meters per second. Let's now consider the horizontal motion. So in the horizontal direction, we want to know what is the horizontal velocity upon impact. Well, that's simple. Horizontally, we've got a constant velocity, no acceleration, so for the entire duration of this projection, there is a horizontal velocity of 20 meters per second. So that's simply horizontal velocity is 20 meters per second. Let's add these two vectors together, and we do so by drawing the first vector. We draw its tail from the object, its starting position, to its head, and then we redraw the second vector from its tail to its head. Once we've done that, we can simply add them together from the start to the finish. This will give us our overall magnitude of velocity upon impact. It's the vector addition of the horizontal velocity and the vertical velocity. So in order to solve this unknown impact velocity, we're going to use Pythagoras' theorem. One side length of right angle triangle, a second side length, and an unknown hypotenuse. So Pythagoras' theorem is perfect to solve this particular problem. So we use the equation c squared equals a squared plus b squared, and we sub in our values. C is represented by the unknown impact velocity, A is represented by one side length of the right angle triangle at 20 meters per second, and B is the other side length of the triangle at 14 meters per second. So we square those values. The 20 squared becomes 400 and the 14 squared becomes 196. Add them together and we end up with v squared equals 596. Taking the square root, that gives us an impact velocity of 24.4 meters per second. Now that's the magnitude, the size of the impact velocity. Finally, velocity being a vector requires an angle of direction. So we have a right angle triangle with 1, 2, 3 side lengths known and an angle that we wish to calculate. Most people can see that trigonometry is the easiest way to solve this problem. From our unknown angle, I recommend we use our two original side lengths, our vertical velocity of 14 meters per second and our horizontal velocity of 20 meters per second. That gives us a tan function, opposite over adjacent. We can transpose that, so we have the angle theta is equal to the inverse of tan given the fraction of opposite over adjacent. Let's sub our values in for this particular problem. So we have the inverse of tan of 14 over 20 gives us an angle of 35 degrees. So to conclude, the impact velocity of a projectile which is fired at 10 meter elevation horizontally with an initial speed of 20 meters per second will be 24.4 meters per second at an angle of 35 degrees decline from the horizontal. Thank you for watching this video. If you've enjoyed and indeed learned something from this video, please remember to like, share, comment and subscribe. And as always, thanks for watching.